Well, I just want to welcome you guys all here. This is our first meetup at our office here. We've had multiple offsite. This is our first here, so I just wanted to welcome you guys to Objectivity headquarters. And the Wi-Fi information is up here on the board. The username is obj_guest, and the password is InfiniteGraph. If you guys are interested, and you might want to download the product if you haven't already, because we'll have a hands-on portion of the presentation later. Also, I'll be asking you guys to download a sample that might be easier to follow along with me. That's on our wiki page. I'll give you guys more information about that in a second.
Excuse me,
yes.
Is outlets working?
No.
Do not, unfortunately, but if you need power, you know, do that. I already put it on the picture. I'll just get you
So just a brief show of hands. I like to do this at all my presentations. How many of you guys have actually used the graph database before? Okay, cool. So most of you guys are new to the technology. I've been working with InfiniteGraph for about a little over 3 years, and before this I was I've been a developer for over 7 years, but I was a mathematician in college, and I was very interested in graph theory. Graph databases, you don't really need to know graph theory, but what you'll find is in the space, a lot of the terminology is more familiar. Some of the algorithms that people use are more familiar if you do have a graph theory background. You don't need to know one, though, to understand this presentation. But I will use some of the terminology. And if you have any questions during the presentation, feel free to raise your hand, and I'll try to get to you. So my goal in the presentation today is to address, to talk a little bit about big data, the movement, database movement, the NoSQL movement. We'll talk about what exactly a graph database is. I'm sorry if you guys are familiar with it already. This might be a little bit of a review for you, but we'll also go into what InfiniteGraph is, what makes us unique. Yeah, I believe so. We'll check. Yeah. And then we'll do a demo and a QA at the end. And if you guys have any really intense questions that you want to ask me. But we'll also have a portion of that will be hands-on. So if you, my goal is by the end of the presentation, you guys leave having written a simple hello graph program, or starting a more in-depth application. The downloading process is pretty simple. You can download InfiniteGraph from this website. We do ask for your basic information so that we can follow up by sending you a license text file, and also that we can follow up with some emails about our wiki page and some more resources. We don't use the information for anything else, so don't be concerned about us sharing that information. Also, if you go to this website, this is our wiki, or our InfiniteGraph developer site, wiki.infinitegraph.com. And you can find a bunch of samples and tutorials on that page. But if you go to download examples or download code examples, it's on the front page there. You can find the flight plan sample zip file, which you can download to follow along with the presentation at the end.
Yeah. So there is Objectivity DB. Do we need that, or?
No, Objectivity DB is our object database. It's another product that Objectivity, the company, offers. InfiniteGraph is a specified graph database product, but we're actually built on top of Objectivity DB. And if you're interested, I can give you some more information about what that means. So NoSQL has been around for, I think, almost 10 years now. The developers started the NoSQL movement because they were looking for other database options. They were embracing choice with a NoSQL, with a open source movement, and kind of the need for old databases weren't really satisfying their use cases with big data. And so they were looking for new technologies that could assist them to answer these questions that they have. It's more than just Dynamo and big table clones, and it's very specialized. So when you talk about, I'll talk more about this, but when you talk about NoSQL databases, they're specialized for specific use cases. So a lot of times you'll get these polyglot architectures that have multiple different types of databases within the architecture that serve a certain purpose within that architecture. But it's very specialized for certain questions. There's over 100 plus projects and products on Wikipedia for NoSQL. And I looked yesterday, there's over 250 meetup.com groups just based on NoSQL. And there's 5 meetups this week, just this week. Today, tonight, tomorrow, and then 2 on Thursday. So you guys can get your fill of pizza and beer. But that's not the only reason why we meet, right? The major reason why NoSQL is so big is because the size of the data that people are looking at, the size of the data. They said, I read yesterday that the number of smartphone users in the world will triple by 2019. When you think about the amount of data that's coming out, what the users expect from these smartphones, what questions they expect them to answer, it's staggering. The idea of big data, though, is it makes big data appear small. NoSQL makes the big data appear small. So if you think about those games where they would show you a picture, but you wouldn't be able to identify what the picture was until they drew back and showed you the context of the picture. It's kind of the same thing, right? With the big picture, it's a little bit too much to get. But if you drill down into smaller problems, it's a little bit easier to handle. So that's the idea of NoSQL. It's kind of specialized databases that make the big problems appear solvable. And it also you encounter a lot of these type of buzzwords around NoSQL: partitioning, replication, distributed queries, distribution, different storage model optimizations, different consistency trade-offs. So a lot of NoSQL solutions have relaxed consistency modes so that you get higher performance. You have the eventual consistency. And then you also have these kind of unique features like query models, dynamic views. And this all helps you to be able to address these requirements for these big data problems. So the key for NoSQL is that these databases specialize in different things. And for a long time, we had one size fits all. Relational databases, you would bring all your questions to those databases. And it wasn't specialized, it was normalized. So we have specialization throughout the world. We have jobs that are specialized. And so the question is, why did it take us so long to get to a specialized database? And there's a lot of different answers to that, but I think the need is what drove us, and then the fact that there was more of an open market is what actually allowed us to answer those questions. Specializing in distribution and deployment, physical data storage, and really unique data models also. So we talked a little bit about this before, but within an architecture, you might have, this is a simple add service, right? You get the cookies, which tell you what kind of user they have, what kind of search history they have. You might have a key value store on the front end that offers up some, takes in user information, and you might have a Hadoop cluster in the back end here that's crunching numbers while your users, searching the site. But within that, you might have a relational database serving up some simple logging information. You might have a document database, and you might have a knowledge graph. So all of these work together to answer different questions, and then that would serve up the advertising to the user. So within a simple API, simple interface, you have all of these specialized databases working in the back end. And you'll see more of these, I think, as we develop our technology and more technologies are offered and implemented. So if you look at the NoSQL landscape, they have their key value stores. You have very high performance needs, high scalability because it's easy to partition key value stores. You have high flexibility because your keys are set, your values can be formless, and there's no complexity here. It's very simple. Obviously, your column stores, similar. You have high performance, high scalability. You have moderate flexibility because you have a simple data model here. And as we go down, we get more specialized. The document store, you have high performance, variable scalability, high flexibility because there's no schema in documents, and then low complexity. But when you get down to graph databases, very high flexibility, usually because of the schema-less part, but then you have high complexity because you're dealing with connected data. And in graph databases, you have a data model that's very unique. You have vertex and edge objects, and you have the connections. So the variability of performance and scalability can be ambiguous because you're buying in the data model and these factors to get the graph application. But you are kind of questioning whether or not it's going to scale, questioning whether it's going to perform for your application. And why don't you, let me just go back real quick. Why wouldn't you just create a graph API on top of these other graph technologies or relational database? People have tried that. And what we found is even just 5 degrees of separation to do a simple navigational query, you get asymptotic behavior as you go out. And we didn't put any names, but open source and commercial RDBMS, you can see basically how it performs up to as the number of nodes and edges processed goes out, blows up. So that's why people are looking more at specialized databases, specifically graph databases. And as you process more data, you want to see this kind of flat performance. So what is a graph database? So most of you guys know relational databases, rows and columns, entries. You can create relationships within relational databases by having certain vertex tables and certain edge connections within those tables. For example, meetings, you might have 2 people that met, where they met, the time they met. Calls, 2 people that called each other, the amount of the time that they called each other and the duration of the call. And then payments, 2 people one person that paid another person, the date that they paid them and the amount that they paid them. And the key for graph databases is the keyword is index-free adjacency, meaning you don't have to look up anything to find the connections. So if you start at Alice, for example, you don't have to look up Bob to find Bob's calls. And within a graph database, with Alice, to find Bob, all you have to do is a simple pointer. And to look at his calls, all you have to do is look at Bob and his relationship. So the index-free adjacency is there's no lookups, that the edges are merely pointers on the vertex objects. So it's very fast traversal as you go through the graph. And the simple 1 or 2 degree queries can be incredibly fast. As you get up to 4 or 5 degrees, it's still only linearly increasing performance. So big data is not always big data. Sometimes people just have very large requirements about how fast the graph data is either written or read. And so some of the use cases you can think about, intelligence and IT, you need to know, these actionable events need to know right away as they come in. And so it presents a very different type of challenge because you're no longer looking at big data processing because of the latency. It takes too long to do like Hadoop processing on top of a relational database. Even though there are solutions out there that are being used, you can think about taking graph data out of a relational database and doing some analysis on it. But it's going to be too slow. You don't have actionable events. Also, a lot of big data requires fast writing. So that's why we talked earlier about the relaxed consistency modes, because when you have a NoSQL database, you want to be able to read and write very fast. And sometimes that means relaxing the consistency of the data to get the data in. And the important thing is relaxed consistency is that the atomic and the durability and isolation are still preserved. It's just the consistency that's relaxed. And so so that makes the writing faster, the write performance faster, but it also allows you to get ACID transactions. You can also partition the data to get faster writes. You can partition the data, the replication, or through sharding, and you could do writes to the partitions instead of writing to a single database. And then you can also defer conflicts. When you have graph data, there's a large number of conflicts because you're writing to data that's connected. So if you update one piece of information, you may be affecting a couple other pieces of information at the same time. So why would you use a graph database? A lot of people ask me that. And the reality is, if you are thinking about problems, graph problems, you probably already know. Relationships are everywhere. Drawing value from those relationships can be very intuitive. For example, the other day I was thinking about who did I go to high school with that I also went to college with, right? And that seems like a very simple problem, but where would I go to get that information? Maybe Facebook would have that query available to me, but those kinds of questions are very simple. And I think as we get more advanced in our technology with our smartphones, we're going to need to be able to answer those kind of questions. People are going to expect to be able to answer those questions. And so AI and knowledge graphs would be very cool. Also, making sense of this data. How do you make sense of all this data? People are going to want to draw information from big data, and this is not going to help. So graph analysis, visual analysis really helps that. So within the graph database landscape, there's a lot of options. You have Neo, Titan, InfiniteGraph, FlockDB, DEX, and OrientDB. Those are probably the most popular, but there are over 30 databases on Wikipedia for graph databases. And you can think about each one of those has their own kind of strengths and weaknesses. Of course, there's InfiniteGraph, which I'll talk about in a second. But obviously, FlockDB has been very tailored to Twitter because it's got a very simple data model, tweets, and so it's high performance for that data model. Titan is built on top of a lot of different open source backends, but they have the same data model on top of each one. So the question is, what are they gaining? What are they sacrificing to be on top of each one of those? And a lot of these questions can be figured out just by looking at the information. Obviously, there's a lot of graph analytics players in the market, and they almost all use Hadoop on the back end. The important thing for all of these is that they are able to partition their graph data. That's very difficult to do. Partition your graph in a very simple, understandable way. And so that's what each of those do. And then you have visual analytics. These are just a few that I thought of. D3 is a really popular open source. Keylines and Tom Sawyer both commercial. InfoViz is also open source. And then, of course, you have some technology built on top of different backends, different graph database implementations. So if you've ever heard of Blueprints or Gremlin, that's a backend. Uses different graph database technologies in the backend. And so you have implementations on top of those. So all of these just show how popular this graph database landscape is. A very diverse landscape. We don't necessarily compete with all of these players. Obviously, visual analytics, we work together with them. Graph analytics, we can work together with them. So I don't think that necessarily you're competing with all these people, but it definitely makes the landscape very colorful. So InfiniteGraph has been around for, I think, maybe 5 years, but ObjectivityDB, which is our underlying object database, has been around since the early 90s, late 80s actually, but our first graph database was built in 93. And it is a complete database management system, so you can think about, because we're built on top of this stable system, and it's an object database, so it's very intuitively works with relationships, because objects, you have vertex and edge objects, right, rather than documents, which are a little bit more ephemeral. And then you also have, because it's a graph specialist, you also have API that's tailored towards navigational queries and edge discovery and vertex and edge algorithms. And so if you look at our architecture, you can see that we have the core, but we also have these features, a navigation API, and we have a custom placement strategy that allows you to do some partitioning, distribution of your data. And that piece allows us to scale horizontally. And so the transaction management preserves the ACID transactions for our database, and we have very significant architecture for graph features. And so I'll talk a bit about that. The idea, though, is that when you come to a database, you're almost always asking only two simple questions. Is it going to give you performance, and is it going to scale? And usually those are very conjoined. And so question for a graph API or graph database is not any different. You're still asking those two questions: does it scale and does it perform? And but there are unique problems for graph database. So the first problem is distributing it. How do you distribute a graph data? There's two ways to distribute. You can have a user distribution, user-defined distribution, custom distribution, or you can have autonomous partitioning. So I can look at your data and see how it's connected and then move it around if certain subgroups are connected. That second problem is NP hard. It's very difficult to do that automatically. So what we do is we allow users to define a custom placement model. And that allows users to place connected data together so they can retrieve it and write it very fast. It's very comprehensive. We also offer things like, indexing, a rigorous caching system, and ACID transactions. Another problem facing graph databases is when you have two applications or more accessing the same connected data piece. For example, this vertex in the middle. You have one application that's connecting vertex 1 and vertex 2 with this edge, right? And then you have another application that's connecting vertex 2 and vertex 3 with this edge. But if both of these are trying to update this edge with this edge information, then you're going to get lock contention. And this happens all the time in graph databases. You're connecting two pieces of data, and that data is shared between two applications. So how do you get around that lock conflict? Well, we have a mode called pipelining, accelerated placement, that allows you to do distributed placement, and it's relaxed consistency, but it also allows you to get around the lock deference that I mentioned and get a high-performance ingest. So that's one way we get around the lock. You could also handle it manually, which which is another way to avoid block conflicts. Just retrying. Using this high performance ingest, though, we get incredible performance. So these are the number of nodes edges per second, and these are the number of processes, and these are the number of hosts. See, as the number of hosts increases, the number of processes increase. You see almost a linear improvement. Another tricky thing is reading with relational databases or key value stores, or even document databases. A lot of times you have these static partitioning, and reading data from different partitions is pretty simple. But when you have distributed graph, right? You have pieces of data that are all connected. So if you want to traverse that data, you would have to go across partitions. It can be very difficult. In fact, Google came up with a solution called Prego, which they encountered when they were doing their page ranking. And you could see that to be able to do a simple navigational query with distributed graph data, you have to do some pretty significant hops. Their solution was to do kind of a map-reduce process to the graph distributed query. When they got to one host, they would wrap up a message and send it to the next vertex, which would tell it, okay, I've got these vertexes. And they would aggregate their data for that step, and then they would send out messages to each of their data, and then they would go to the next step and then aggregate their data, and then send out their messages and aggregate their data. With navigation, though, high-performance navigation needs to be low latency, which means that you have to optimize around this use case. And so we have something called distributed navigation, allows you to do a few different things. First, it detects local hops so that you're not sending messages when it's all on the same machine. You're caching it. You're doing it in memory traversal. And then when you are going across partitions, it does route tasks to something we call a query server, which allows you to do something similar to Prego in the sense that you're sending a message across. And when you have frequently accessed remote data, it also locally caches it. So it's very intelligent. And this allows us to get a very high-performance navigational query. We also have a super simple API, which we'll actually get to play with a little bit. You create your Java objects, which have your schema in them, and then you're adding that vertex to the graph. Similar with edges, you have your Java objects, which represent your edge, and then you're adding the edge to the graph or to the vertex. So you can call add edge to the graph and pass in both vertex endpoints, or you can call add edge on the vertex and then just add the endpoint. You also have to pass in the direction. We support both incoming, outgoing, and bidirectional edges. And then we also support a weight, which is given here. And the weight can be used on navigation, so you can do kind of a weighted navigation. The key between vertex and edge objects is vertex objects extend our base vertex type, and edge objects extend our base edge type. So when that is visualized, you have Carlos paying Charlie, you have Charlie paying Bob, you have Bob calling Carlos, and you have Alice meeting with Bob. So it's a pretty simple graph. Our traversal can be very complex or it can be very simple depending on your needs. So we have these default strategies, breadth first, depth first, which are what we call guides. And then we have custom qualifiers and custom result handlers, which allow you to do very complex navigational queries. We are a schema solution. We're working on property support, so allow you to do optional properties on your schema types. But we are a schema solution, which can be seen as being a negative because It doesn't allow for full-on flexibility, but it's also positive in the sense that, when you don't have a schema, you can run into some very significant bottlenecks. First, the most obvious is just indexing. You have to use indexes to look anything up. But in a schema solution, you can use a query system. You can place by types. You can shard very simply by value, and you can place by related, which all those support. So, and then the final thing, optional properties supporting a property model. We will release that in not the next version, but the version after. And we're going to be working on these hybrid model, which you have your schema, Java class schema, and then you also have these optional properties that you can set on the object level. With other types of graph databases, you have to set all properties on the types, and so it's a little bit more tricky. Another advantage is to using schema is what we call graph views, and these are used in navigation to filter by type. So if you think about your navigation, sometimes you have a lot of types that you care about, and some types that you don't care about, because sometimes you're asking your knowledge graph different questions. And so you could think about this simple case, the Kevin Bacon problem, right? You guys know the Kevin Bacon problem? So in the Hollywood movie scene, say you want to connect Kevin Bacon to another actor within 7 steps of degree of separation. And so when you're answering those kinds of silly games, you want to be able to use popular movies. So one way to get around this question is using a graph views. If you have, say, like the IMDb data set, you can use graph views to filter out TV shows. You can use graph views to filter out made-for-TV movies or made-for-video movies. And then you can use graph view to exclude. He's got these cases where he's hosted or he's showed up in a show by as himself, like in a Jay Leno or whatever. And so you want to filter those types out. So we have TV shows gone. We have made-for-TV movies gone, and edges that he appeared as himself in. And so then you're stuck with popular movies like all of them too. And so graph views can be very helpful when you're talking about complex navigations. We also have a visualization tool. You might have noticed when you downloaded the product, if you downloaded it, and it asks you if you want to install a visualizer. All right, so that brings us to this part of the presentation where we'll actually be walking you through an installation and a sample. Is there any questions before we move on? All right. Do you want to take a couple minutes? Okay. Should we
grab some of the cheese pizza before we run out?
Yeah.
Less than 1 minute.
Why don't we take a couple minutes, and if you guys want to grab seconds, go ahead. If you want to go to the bathroom, feel free. And they'll come back, and then we'll talk more about installing and the sample.
Should probably be the slide up with a link to
Oh, yeah, definitely. I'll post that. Yeah, sure. No, it's a good question. We do have, we're working on it currently, and probably will be rolled out in subsequent versions. We have a version later this year. So we'll have pieces in there, but we don't have a full-on clear ledger this time.
typical error was when you were installing. Right. Let me just check with Nick. Hey, Nick, on Windows, JDK 1.7 is fine, right?
On Windows?
Yeah.
Well, yeah, 1.7 is
yeah,
fine.
right. He got an error during the installer. I didn't see it, but now he's not able to launch Visual. Yeah.
1.6 is not fine?
Yeah, they're installing 3.1. And it is the 64-bit. And actually also, when he launches Visualizer, it says not a valid Win32 application, which is strange. believe you can download the 64-bit version.
So let's.
But we may
Let's
not
talk
need
about this. Yeah, we may not. But let's talk about this a little bit.
Okay, this one.
I'm sorry. I can post it, or we can send it to you. And of course, you can always email me. I can send it to you directly. Sure, sure.
We should not need
The application that we are downloading is it just for Mac?
it may be fine.
Yes.
Excuse me, whether it's for Windows or it's for Mac.
It's both Linux, Mac, and Windows.
Right, but we should ask
Yeah, we're going to use Eclipse, but you don't have to have Eclipse. So you can use NetSuite or any Hey, can you ask T if he has an installer on a zip drive? See if he has an installer on a zip drive? Yeah.
That would be good. But Nick, are they actually writing the code or are they just running the existing code? Because they could do it in the AntiScript, right?
We're going to run existing code, and then after, if you want to write some custom code.
Okay, so it's not
Just a second.
okay, right. So wiki.instagram.com.
Yeah.
So I'll write it up on the
So if you guys haven't already downloaded the sample, what you can do is go to our wiki page, which is wiki.infinitegraph.com. And off to the side down here, you have download code examples. If you select that, it'll take you to this page, and you see the flight plan sample zip here. And once you download that, you can extract it to some file and then open it up in your desktop or in a directory somewhere, and then import the Java project into your IDE, whatever you're using on. So I'll do that now. You have I have the flight plan sample on my local desktop. And I'm going to. So what you'll see is that it can't compile initially, and so if you configure your build path, you can add just all that it needs is the InfiniteGraph jar.
Only one?
Yes. It's okay. So we also support SLF4J implementations. We have a simple JDK implementation that we distribute. We also have a simple SLRJ implementation. So you can go to our distribution and select like the SLF4J JDK, which will be Java util logging, or a simple, which will just be console logging. And so that's a requirement for SLF4J. So InfiniteGraph is our core, and SLF4J is just one of the implementations of SLF4J. So that's the two that you'll need. We should see it compiles now. So let's just take a quick, go ahead.
Can you show this again on a weekend where you took it?
Oh, sure. Sorry. I don't need to rush through that. But, so you have a build path. You add external jars, and then you add the InfiniteGraph jar, which is our core. And then you add a SLF4J implementation. We either have Java util logging, which is JDK 1.4, or SLF4J simple, which is the console logging. And so I selected the console logging. So basically here you have some base types. You have airport and flight, which are my edge and my vertex objects. I'll show you that in a second. And then you have a create DB class and a run DB class. So your base types, this is your schema. We define our schema through Java. So you can define any types here, primitive types. We support all primitives and arrays of primitives and dates, date time. And so we have the airport here setting a vertex base type and having one field, string field called code. And then your flight class extends our base edge type, and it has an int, a float, and 2 dates. You also might notice we have this method we call fetch and mark modify here. That just tells you to read or write to the database. If you're writing, like in a set method, you add that mark modify to write, and then fetch reads it from the database. If you don't call those methods, sometimes you can't have stale data. All right. So basically, both these, I construct the object when I set the code when I construct the object. I set the fields when I construct the object. So when I create the object, all I'm doing in this class is I'm calling one method called main, which deletes the graph if it exists, and then creates it. So deletes it if it exists with that DB name. The DB name is all you need to create a database, and to delete it is the name of the database you want to create. And you can optionally put in this property file, which has some configuration for how you size your cache, or how you want to, the mode that you want to use for ingesting edges, so you can set up that pipelining system that I mentioned before. And then create, all you need is the database name, but they also put the property file, which has some configuration. So let's take a look at the properties file really quick. So in this properties file, all it has is the boot file path. So we have something called the boot file, and that's the only thing that's required for your database. There's other database files that are created, but this is all that you need to create a database. It'll use your current working directory if you don't give it a boot file path, but in this case, we give it another boot file path, which is the data directory. So the database, if you don't use this properties file, it will be put in your current working directory, but because we passed this in, it'll create a database inside this data directory. Okay. So if I run that right now, it says I can't open the boot file because it doesn't exist. So that warning is a little obvious. But then down here it says create a new graph database. And if I open up my data directory and then refresh, there it is. So you see I have a boot file, FTP file, and some configuration of data files. So these are all default databases.
So where does a license file go into this?
Oh, that's a good question. So if you guys get a email after you download the core, if you place it within the installation directory, so for example, I installed InfiniteGraph in my program files directory, and in the 3.1 folder inside my InfiniteGraph installation, I have my license file here. So you can place it here inside the installation directory, but you can also place it in your desktop, on your in your system 32 directory inside Windows, and so it'll look in all those locations. So so let's go back. Go ahead, sure.
So if I were to build an application that uses this jar and the graph, and I host it on a server, than if I put the license file in the same the installation directory.
So, so we also have binaries too, native binaries, and so it uses the same installation directory to find them. So these binaries here are C++ binaries, so you want to make sure that we can find those. So the database is created here, and then let's take a look at the launch, the run file. So the run file is basically trying to calculate, okay, my model, my airline connects certain airports to certain flights, and those flights go to other airports. And so I have my graph, and so we're going to create our graph here, create data. And then our goal is to, from that data then, find the cheapest flight from one airport to another airport. So it's a simple kind of algorithm that all the airlines use now. You can find the quickest flight, you can find the cheapest flight from one airline, one airport to another airport. It's probably a lot more verbose data, but let's take a look at the create the data method. So in this data we have 17 different flights. We have flights that have these dates for departure and these arrival. And you notice the time of departure and the time of arrival is embedded in the date. These are the airline code, airport codes for both names. So down here you can see we create, for each of these flights, we create databases if they don't already exist in the database. I'm sorry, airports if they don't already exist, and we name them. So this is a way to look up your vertex objects very quickly by naming them, and then we add edges for those corresponding to each of the flights. That include the flight's name, the flight name, the flight arrival time, and then the departure time and the arrival time. And this final float is the price. I didn't show you that, but if you scroll over, you'll see this is the price of each of these flights. So you add vertex objects if they don't already exist. If they do exist, you just skip that, and then you add an edge to those vertex objects. Airport, arrival, departure, and arrival. And these edges are all bidirectional, or outgoing, sorry, outgoing. And then you're also embedding the value of the flight as the weight. All right. So then the find cheapest flight is a simple algorithm. You have a transaction that started that's read-only. You're getting your departure and arrival airport from the code that you pass in to the method, and then you define what we call a path results handler, and that'll handle your navigation results. You're also using a custom guide because it's sorting by departure date. If you use a custom guide, it'll basically order the navigation where you want to start first, going out from your start edge, or start vertex. And so in this case, a custom guide will order them by departure date. And then we're using what we call a Java-only policy here because we have a C++ RA navigation relationship analytics engine in C++. And it's high performance, but sometimes when you're using custom guides, you have to use a Java-only navigator, which is usually not the case. But if you use like breadth first or depth first by default, then you don't have to use this policy. The result qualifier basically will qualify based on the target airport that you want to arrive at. To start the navigation, all you're going to do is call start, and then you can execute that to the result handler, calculation, and it just prints the results to the console. So let's go ahead and run that. So it's printing out the flights that it found, and then it prints out the cheapest flight out of those 4 that it found, and the price, which would be $1,835. So basically, the first flight here is the cheapest one. So that is our sample. So you'll notice too, once it executes, you'll see some new database files here, your edge file and your vertex file. We didn't use custom placement here, but if you use custom placement, you can partition this data to other hosts, to other file directories, and it allows you kind of some nice logical partitioning. All right. Is there any questions? So with the rest of the time we have, if you guys want to stick around, if you go to our wiki page, there's also another sample called Hello Graph. And if you open that within your IDE, that's a good place to start for writing your first graph application. So inside the Hello Graph file here, you have a simple main method. And what you can do is just take out the code that's in there, which basically adds a couple person and meetings, and then just replace it with whatever classes and whatever calls you want to make. So what we'll do is we'll just be around, answer any questions you guys have, but if you'd like to stay and work on that, you're welcome to. But again, I just want to thank you for coming, and if you have any questions, feel free to stick around. Have a great day. So it's a 60-day free trial, and then after that, it's basically based on the use development or distribution, and then it's very flexible based on how many record or basically it can be configured by how much you're going to use.